This is a lesson on applying Gauss's law in the University Electrostatics unit. Calculus-based physics we're looking at here. So in a prior lesson, I wanted to highlight that we had talked about what electric flux is, the basic concept of electric flux. I think if you do not understand the basic concept of electric flux, you're going to have trouble with Gauss's law, because that's part of the formula, that's part of what Gauss is looking at, is how much electric field is passing through a surface. At a simple level, if the electric field is constant over that surface and the surface is kind of simple, we can just find an electric flux E dotted into a dA vector. We don't need to, or actually an A vector. We don't need to integrate, right? So in this situation here, we just know the area of the surface, we'd know the electric field, and we'd evaluate the dot product. So that's the basic concept of electric flux. When we expand out with Gauss's law, we're going to look at a more complicated surface. We are going to look at simple, complicated surfaces, if that makes any sense. At introductory level, we introduce a small subset of surfaces that are very nice to look at. The one I have shown here is spherical. And when we look at the dA vector, that's why I picked this out. I kind of wanted to highlight the dA vector. We care where the area vector, and note over on the side I talked about there's an area vector. We think of it in terms of the normal vector to the surface. So if you have sort of a flat surface, you would think of a normal vector. With any sort of radial symmetry, such as spherical or cylindrical, you would have a radial vector. All right, and we want to know, we're really looking for all parts of the electric field that are parallel in that direction, the normal to the surface. Okay, so we have this hairy ball over here. That's what we call this, hairy ball with all the normal vectors pointing out, and we want the electric field in that direction. And if you know, we know about electric field from charges. If I just have a simple point charge here, maybe it's a proton or something, the electric field points out radially. And so that's the direction of the electric field. So what Gauss allows us to do, or this is the electric flux, right? I could still look at just the electric flux passing through this surface. There's an electric field. I choose a radius, I can integrate over that radius, and I can get some amount of the electric flux passing through that surface. That's what electric flux is. So Gauss took this a step further, and you're going to see the change in this formula over here on the top right, where we have accounting for the electric flux. This is the electric flux portion that we've looked at. And also Gauss said, well, if we're looking at some sort of closed surface, some sort of surface that is completely encapsulating a charge, then the flux passing through that surface is going to be related to the charge enclosed by that surface. Okay, and that is Gauss's law, is there's this relationship. And again, this is still review. If you look back at the electric flux and Gauss's law lecture that I had put together before, I kind of do some hand waving here on this slide and derive the electric field due to a point charge. What we do is we pick a nice surface where the electric field is constant all over that surface, and then we know the surface area. We have spherical symmetry around a point charge, like I mentioned, and there's the value of the point charge. We have an epsilon naught, and we get the equation here. And so that's a very, I think, easy example, very basic that we introduce. I'm going to remind you that any electric field inside a conductor is zero. That may be some tricky part that they can put in problems as you work through problems involving this. Conductors, you know, all of the charge resides on the surface. If you're looking at an insulator, the charge will reside throughout that material, and it may be uniform, or you may be given a charge density formula, a function with respect to position. Okay, so the amount of electric field passing through a closed surface depends on the amount of charge enclosed by that surface. And we're going to use a judicious choice of symmetry. We're going to look at spherical, cylindrical, or planar. Okay, those are the nice symmetries that we choose at introductory level. And if you're at higher levels, a physicist will always try to choose the simplest situation as best as possible. It could be that, like, you have a potato-shaped charge distribution, right? There's some sort of weird thing going on, and none of these symmetries really fit it. And so at introductory level, we're not going to do anything weird like that. We're going to always choose a nice symmetry. And what nice symmetry? How do you know what symmetry to choose? That's a legit question, right? And when we look at choosing the symmetry, what we're doing is we're choosing what we call a Gaussian surface. Okay, right? When we look at this integral over here, we need to choose a closed surface. That's what this integral means, right? An integration over an area, that means that it needs to be a closed surface. And so, since we're trying to do an integral easy, the easiest way to do an integral is if one of these values is a constant value. Well, the area always depends on the radius of our surface, so we can't make that too much easier. What we're going to do is we will always choose a Gaussian surface over which the electric field is constant. Okay, so I can write that out here. The E field is constant over all of the surface. So again, when we're thinking about, this is an example of an insulator with some sort of charge density throughout it. You could be just looking at a point charge. A point charge also requires a spherical symmetry. You could have some sort of charge distribution. You might have a couple of charges, and if you get far away from it, some distance r, you could also just encapsulate those charges within a nice circle. That's meant to be a circle. And just look at the electric field at that point, and if you're far enough away, then all of those charges collapse down to just one charge, and we'll assume over that surface the electric field is constant over all of it. And at this point you're working with integrals, you know that any constant within an integral can actually come out, and that's what we're going to emphasize. That's what I'm going to emphasize in this lesson, is integrating over a surface area where the electric field is constant. We'll bring it outside the integral. It won't be anything interesting going on. It'll be a really easy integral to deal with, and we should be able to get some answers pretty straightforward that way. So there's a spherical symmetry. You're looking for something that has a radial electric field, and at some distance r, the electric field is constant for all values of r. Okay. Again, when you look at cylindrical symmetry, if I want to choose like this point away from, this might be a wire. That's usually typically where a cylindrical symmetry comes into effect, is a wire. And, for any radius, all right, there's a radius. Away from there, the electric field is going to be constant for all those points that radius away. We need to contain some charge, so what we're doing is we're choosing a cylinder, all right? So there's our cylindrical symmetry. We know how to find the area of a cylinder, all right? And it's just the outside here. The electric field points radially outward, so we won't have any electric field passing through that area, like the top and the bottom of the cylinder. It'll only be pointing out radially, so we'd only need the area of the barrel of a cylinder. Okay, so cylindrical symmetry. The other one we have is planar symmetry. You can see that this is some sort of surface density, surface charge density. It's over an area. Okay. And what happens is in order to create a closed surface, what is done is we choose some sort of area here, and then it goes down, and then it intersects the area, and then it goes down onto the other side. So when we look at the electric field, they might call this like an infinite plane of charge. All right, that's typically what they would call it, is an infinite plane of charge. And what happens is the electric field points outward from this side, and it points outward from the other side. It's just straight outward from the plane. And so in order to have a closed surface, we're going to have, we're basically creating a box around both sides of the plane, right? There's going to be an area on one side, and on the other side of this plane, there's also going to be an area on the other side. I don't think this is a very interesting situation. I mean, it's not a very interesting integral anyway. I can do it real quick here. As an example, all right, if I'm applying Gauss's law, the electric field at some distance, I don't know what you want to call it, X or R, whatever position you have away from this surface, it actually doesn't matter. If you're close enough to the surface, being this far as opposed to this far, it's a constant value. And to set up this integral, we go the integral E dot dA, and we know they're in the same direction. There's the E pointing upward, the area vector also pointing upward. So we'd have a cosine 0 in here. That's not very interesting. I'm not going to put it. So I've already evaluated the dot product over the closed surface has to equal Q enclosed over epsilon naught. Because we chose a surface where the electric field is constant, I'll bring that out. The area that I chose, well, that's actually pretty trivial. I can see that there's just two of these areas here. Q enclosed, if I look at Q enclosed, I have some surface charge contained right in here by the box. And so to find the charge enclosed, I would take sigma and just multiply by that area. And then I still have epsilon naught underneath. And so this is what I'm saying. It's kind of a trivial equation. Near an infinite plane, you get sigma over 2 epsilon naught to be the electric field on either side. Okay. And again, notice that this integral, right, when I bring the electric field out, I get the integral dA. And what I'm saying is you're going to choose a nice surface, a nice Gaussian surface, where the integral dA is well formulated. I know how to find that area easy for a plane. I know how to find it easy for a cylinder, and I know how to find it easy for a sphere. Okay. And I'm just going to highlight these steps again. Gauss's law strategies. Select the appropriate symmetry for the charge distribution. You're going to look at the charge distribution. You're going to look at the shape of your charge distribution. At an introductory level, we're going to make your choices pretty easy: spherical, cylindrical, or planar. Do I have something sphere shaped? Do I have something wire shaped? Or do I have a plane? It says choose and sketch the Gaussian surface. So that's something that you noticed I did on the previous slide here. I drew my Gaussian surface here for the planar. That was my Gaussian surface. I have an area here and an area here. That's my Gaussian surface. Here's my Gaussian surface here. All right. The Gaussian surface for this one would be a sphere just around this charge distribution. So I like making sure that you choose and sketch the Gaussian surface so it's very clear to you what the surface is. Okay. And it should be a nice one, nice being that we know how to formulate the area of it. The electric field, most importantly for the Gaussian surface, should be constant over that whole entire surface. The electric field is constant. You can't use a cylinder around a sphere because the electric field won't be constant over that cylinder. So make sure the electric field is constant over the surface. And again, the surface area should be easy to formulate. We're doing spheres or cylinders or boxes. Okay. The issue about the other side of the equation, right? So that deals with this side of the equation, the electric field in the area. The other side of the equation needs you to find the charged enclosed. It may be just a simple charge that you're able to just put a value in there. You may have a more complicated situation. And, you know, on the previous slide, I had to say the charged enclosed is a surface charge density multiplied by a surface area, right? This is finding the charged enclosed. Use the charge density with correct dimensionality to calculate. Once you know that stuff, you can set up the integral relating the electric field, Gaussian area, and the expression for your charge enclosed and simplify algebraically. At this point, you're not really doing an integral. What you're doing is you're integrating over a known area, so you just know the formula. The result of the integral is the formula of an area, okay? So I think Gauss's law looks intimidating on the left side with the integral E dot dA. But for me and all my experience, and when you look at problems, the harder part of this problem will usually be finding Q enclosed because of different shapes and charge distributions that you may be given on your problems to work. Okay. Once you get to step 5 here, evaluate the integral. I could even say like evaluate. That means put in the right formula for the area. And then you're going to have probably some variables on both sides that may cancel. We'll see that in the problems that I choose today. The first example problem I chose today for us is one that's dealing with 5 concentric spherical shells. And when it says shell here and it doesn't give me any dimensionality of the shell, I'm going to assume that they're thin shells. That the thickness of these shells is very, 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 very small compared to these distances: 1 meter, 2 meters, 3 meters, 4 meters, and 5 meters. Okay. So if I drew a cross section of the shells, all right, we have 5 of them. And please forgive me for not having perfect circles here. Is that 5 of them? I think that's 5. 1, 2, 3, 4, 5. Okay. And each of them are marked at 1 meter. Each is uniformly charged with 5 nanocoulombs. So on the inner shell of 1 meter, there's 5 nanocoulombs on it, okay, all distributed evenly around on that spherical shell. There's 5 there, there's 5 there, there's 5 there, there's 5 there, and there's 5 there. It says, what is the magnitude of the electric field at a distance of 2.5 meters from the center of the shell? So what I'm going to do is I'm going to note my symmetry. My symmetry here, I think, is pretty clear. We have spherical symmetry. Okay, so I'm going to identify that my Gaussian surface needs to be spherical. It needs to be a spherical shell. Okay, spherical Gaussian surface. I'm going to draw that on my picture here. And we're 2.5 meters away from the center, so that means we're between the second and third shell. So 1 meter, 2 meter, 3 meters. So we're in here. There's my Gaussian surface. As, you know, circular as it can be, it's representing a sphere of radius 2.5 meters. Okay. When I'm looking at this, I did this. We have spherical symmetry, so the electric field will be constant over it. I have a spherical shell. I need to worry about charge enclosed. And I think that's where you're going to realize at some point in this problem, if you're looking at the charge enclosed by this Gaussian surface, you're going to note that the 3rd, 4th, and 5th shells are outside the Gaussian surface. So to me, this is some maybe extraneous information. If we're looking at the electric field at 2.5 meters and we only care about that charged enclosed by the surface, the Gaussian surface. We don't need that outer shell. We don't need that shell at 4 meters, and we don't need that shell at 3 meters at all. It's superfluous information. We don't need that charge. When you think about it, it's spherical symmetry. The charge outside would be contributing to electric field at 2.5 meters, but there would be spherical symmetry such that it canceled out. And all parts of those electric fields would cancel out and not contribute. So we don't need to worry about those outside shells. I think it looks like an intimidating problem, like 5 concentric spherical shells, but applying your knowledge about the spherical surface and charge enclosed by that spherical surface, we don't need those charges. Okay. So let's set up this integral. Do I have everything going on? Yeah, I have everything going on. Charge enclosed, I'm given it. It's a straight number. All right. I don't need to worry about any charge densities or anything like that. So let's set up our integral, and I'm going to put the E outside. Right? Because we chose a nice Gaussian surface, the electric field all along this green circle here is going to be a constant value, and it's going to come outside the integral. E dot dA equals Q enclosed over epsilon naught. So inside Q enclosed, we're going to have the charge on the 1 meter shell and the charge on the 2 meter shell. So we're going to have 2 times 2.5 nanocoulombs divided by epsilon naught. The electric field is what we're trying to calculate. The integral dA over this surface is the surface area of a sphere. We have spherical symmetry, so we're going to have surface area of a sphere. 2 times 2.5 is, oh, I made a mistake. Hopefully you caught that. 2 times 5 nanocoulombs is going to be 10 nanocoulombs. So I could even put a number in for that if I wanted to, but I'm going to leave it there for now. I'm going to plug in my numbers in the last step here. Okay. All right. So this is, I evaluated the integral. Did you see me do that? It was so slick. It's such an intimidating formula. And then if you choose the right Gaussian surface, you're not even doing an integral. You're just saying, oh yeah, it's a sphere. It's the surface area of a sphere. We're accounting for charge enclosed. Epsilon naught is a universal constant. So when I get this going, I'm going to have 10 times 10 to the negative 9th. Nano is 10 to the negative 9th. I'm going to divide by epsilon naught. Epsilon naught is 8.85 times 10 to the negative 12th with some units that I'm not going to get into. We're going to have a 4 pi, and we're going to have an r squared down there too. So that's where the 2.5 goes, 2.5 squared. And when you run this through your calculator, you're going to get 14.384 and some change. It has units. Electric field has units of newtons per coulomb or volts per meter. I've talked about that in a prior lesson. And that's how you do that. Let's do another example. I chose another one. So here we just had thin shells. I assume they're conducting so that the charge is evenly distributed over them. In this situation, we're going to have the electric field of a spherical insulator. And so what they tell us is that a spherical insulator has a radius big R. We can see that over on the picture here. Picture says big R, 0.24 meters. All right. And is uniformly charged. It's an insulator that has a volume charge density. Do you see that? It's coulombs per meter cubed. So that's a volume density. So it's constant throughout. It's like a mass density. It's just the charge is evenly distributed throughout the volume of the sphere. It asks what is the magnitude of the electric field at a point that is half the radius, and 3 times the radius. So notice that we're inside the sphere, we're at the surface of the sphere, and then we're outside the sphere. We have 3 different parts of this problem to work on. Okay, so let's see if I can get this all on the same slide here. I have a lot of room. So first step, identify our symmetry, might be pretty easy to note. We have spherical symmetry. Okay. For part A, I need to identify my Gaussian surface. The Gaussian surface is going to be a sphere of radius 0.12 meters. So I can draw that over here. I'll draw it in green. There's a radius. There's A, right? 0.12 meters. Okay. And the big idea here that I've emphasized is the electric field is constant over that whole surface. We know the surface area of a sphere. We did that, in the previous problem. We had spherical symmetry. So that takes care of sort of this side of the equation, the left side of the equation. We need to worry about Q enclosed. When we look at the charge enclosed by the Gaussian surface inside the radius of the sphere, we're going to have that much charge enclosed. Okay, so when I look at Q enclosed here, I'm going to have rho times the volume of that Gaussian surface, 4/3 pi times 0.12 cubed. I'm just going to put an r cubed here. You're going to see in a minute why I'm going to want to leave it in terms of r. So in this situation, in order to find Q enclosed, we're going to remember that we don't have all of the sphere. We only have part of the sphere inside that Gaussian surface. Okay. So let's set up our integral and evaluate it. E is a constant value. I'm going to bring it outside the integral. E, the integral dA. Rho 4/3 pi r cubed. We're going to note that the integral dA, again, because we have spherical symmetry, is 4 pi r squared. Let me not forget my epsilon naught term. Rho 4/3 pi r cubed divided by epsilon naught. I'm going to do the simplification that I mentioned before, simplify as possible. There's a 4 on both sides. There's a pi on both sides. This r squared cancels out all but one of those r squareds. And when I simplify this formula, I get the electric field equals rho r divided by 3 epsilon naught. Okay. Again, really slick integral. We know the surface area of our Gaussian surface. All right. We had already dealt with our charged enclosed, and now we can do a calculation where I'm just going to plug the numbers in here. 10 to the 2.8 times 10 to the negative 6. The radius we're at, 0.12, and divided by 3 times 8.85 times 10 to the negative 12th. You run that through your calculator, you get little less than 13,000 volts per meter, newtons per coulomb, something like that. Newtons per coulomb is the electric field. That's how you do that. All right. Let's do the next part, part B, where we have the radius at the radius of the sphere. So again, we still have spherical symmetry. We're going to have to choose our spherical surface. I'm drawing it in blue over here. It will be a sphere of exactly the charge that we have, of radius big R. That will be our spherical surface. So when I look at Q enclosed, I'm going to have the same situation, rho times 4/3 pi r cubed, and the r in this situation is not going to be little r, some little r within. It's going to be the big R, the radius of the sphere. The whole sphere is inside our Gaussian surface. So we want to account for all of the charge that's on the sphere, in the sphere. Okay. So we can do this again. E, the integral, dA equals rho 4/3 pi r cubed divided by epsilon naught. Our area is the area of the Gaussian surface, which is 4 pi big R squared. And you're seeing lots of similar things. Maybe it feels like deja vu from the previous problem. Do you see that? I'm going to do, again, some algebra on this guy. 4's cancel on both sides. Pi's cancel on both sides. Factor of r squared cancels all but one factor of r there. And so the electric field at radius big R is going to be rho big R over 3 epsilon naught. Okay. I can plug numbers in and calculate it. And you're going to notice, right, if we're inside the sphere, it's the same as if we're at the surface of the sphere. And this is because it is an insulator with a uniform charge density. Okay. And when you calculate this, you should get twice as much as the electric field before, 25,305.65 newtons per coulomb, or volts per meter, whatever your favorite one is there. Okay, so that's the electric field at R. And don't get too excited. You're not going to be able to use the same formula outside. But let's set it up. So outside the sphere, at C, I'm going to have a Gaussian surface of radius R. And this can be like R3. I'm just going to call it an R in general. There is a general R. Okay. And when I look at Q enclosed by this third Gaussian surface, the black surface here, I'm going to note that all of the charged sphere is within that Gaussian surface. So it's going to have the same amount of charged enclosed as part B in this problem. Right? I'm getting all of the charged enclosed, so it must be all the way out to the big R value that's charged enclosed. I can set up my equation with the integral. Integral dA equals rho 4/3 pi big R cubed over epsilon naught. Okay. So now we need to plug in what the area of our Gaussian surface is. And when I look at this Gaussian surface, it's going to have an area of 4 pi little r squared, this little r that I've defined to be the radius to C. It could be any radius, past C. So I'm just using little r to represent it. We're going to still have the charge enclosed, which is determined by the outside radius of the sphere, the big R cubed, epsilon naught. I'm going to simplify this yet again on this problem. 4 cancels with 4. The pi cancels with pi, but the r's do not cancel because they are different r's. They're different r's in this situation. Okay, so when I get the formula for this electric field, I'm going to have a rho. I'm going to have an r cubed. I'm going to divide by 3 epsilon naught little r squared. So when I run this through, when I put all the numbers in here, I'm going to get 2.8 times 10 to the negative 6th times 0.24 cubed, right? That's the outer surface of the charged sphere. 3 epsilon naught, 8.85 times 10 to the negative 12th. And then my r squared is to the point that I'm looking at, the little r. So that's 0.36 squared. Okay. And when you run that through the calculator, you should get, it's decreasing overall outside of that sphere. As you get farther away from the sphere, it'll get smaller and smaller and smaller from that 25,000 value. It's 11,246 and some change, 0.956 newtons per coulomb, volts per meter, whatever you want to put in there. Okay. So, I like this problem in reflection. I like this problem because it exemplifies how to find different charge enclosed. You can see that the charge enclosed is different for the first part than for the second part. And the third part and the second part have the same charge enclosed because we're at the surface of the sphere or we're outside the sphere. All of the charge is enclosed by the Gaussian surface. The next example I've chosen for you is a little bit more complicated. Again, we're going to see that it's not the integral side of the formula, the E dot dA, integral E dot dA, that's the hard part, but it's the Q enclosed that's going to be the hard part. What is Q enclosed? So when we look at this, I'm going to read the statement and get a picture going. It says a sphere of radius r equals 3 meters has a non-uniform charge density that varies with the distance from its center as given by rho. Let me put a rho in there. AR squared, where A is some constant value. And R is less than little r. So if I think about a sphere, and so we've done step 1, like what's the correct symmetry here? It's spherical symmetry. All right. So here's radius big R. For little radius r, some point inside, right? Some little r radius. The density at that radius is given by this function, some constant times r squared. What is the magnitude of the electric field at a distance 2.5 meters from the center? So we're not all the way out to the edge, but we're somewhere between the center and the edge of this. We haven't contained all of the charge that is in the sphere. So we're going to have to do some work in order to find Q enclosed. I've dealt with this. We've chosen a Gaussian surface where the electric field is constant. I have a sphere, so when I do the integral E dot dA, the integral E comes outside. I just have the surface area of my Gaussian surface, and then I'm going to have to do Q enclosed over epsilon naught. And this is actually where it's going to get complicated on this problem. Okay, because if I want to find Q enclosed, all right, Q enclosed, I am going to have to integrate over a volume for that charge density, volume charge density. It's not constant. As it moves outward, that density is changing. And I can't just go AR squared times, whatever that volume is. That's too simple. That's a nice assumption, but that's too simple. Because that gives you maybe the charge at that, but you need to integrate from 0 to that radius in order to get all of the charge contained within that. So when we do this integral, we're going to go from 0 to that r value dV. Okay, so this becomes not terrible of an integral. I know it may be a little bit hard to put together. When I look at dV, okay, because I have spherical symmetry, I'm going to have the surface area times dr. So I'm going to say dV is going to be 4 pi r squared, right? That's the surface area. And then we're going to say that surface area is dr thick, okay? And that's true for all r. So when I put this integral together, with knowing this, I get the integral of from 0 to r. Our volume charge density is AR squared. And then I'm going to multiply by dV, which I know is 4 pi r squared dr. That's how I'm going to be able to find my Q enclosed here. Like I said, more work. And I said this from the beginning. It's not the integral side of the equation that presents trouble. It is the Q enclosed that typically presents the issues. Finding the charge enclosed by your Gaussian surface. So let's do this integral. Let's see. I have a 4 pi. Those are constants. I'm bringing it out. The A is a constant as well. I'm bringing that out. I'm going to get the integral from 0 to r of r to the 4th dr. Okay, so at least it's not a terrible integral. I can integrate a power rule. So I'm going to get 4 pi a. This thing becomes 1/5 r to the 5th evaluated from 0 to r. Or in this situation, you could actually plug in this to be 2.5. and that's going to be our Q enclosed. Okay. So I'm going to put that information over on the right side of the equation, Q enclosed over epsilon naught. 4 pi a times 1/5 r to the 5th divided by epsilon naught. Notice the other end is 0. I'm not really interested. I mean, you plug in 0 for r and you get 0 out of it. So we really just care about what is the value at that r value. Okay, so let's keep working on this. The integral becomes trivial. We have a spherical symmetry, so we're going to have the surface area of a sphere at radius r. We still have this other stuff over on this other side, 1/5 r to the 5th over epsilon naught. I'm going to do cancellations. We have a 4 canceling on both sides. We have a pi canceling on both sides. And we have an r squared canceling out 2 of the r to the 5th. So we get r cubed over there. So then we're going to say the electric field at some radius r, where r is less than r, is given by this general form, a r cubed over 5 epsilon naught. You can plug numbers in. 1.9 nanocoulombs times 10 to the negative 9th. There's some units going on there. You can see they cancel out. We have meters to the negative 5th, and then you end up with meters squared on the denominator. It works out fine. 2.5 cubed divided by 5 times epsilon naught, this universal constant, 8.85 times 10 to the negative 12th. And when you run this through your calculator, given E at 2.5, you will get 58 No, I disagree with that answer. I got 160 something newtons per coulomb or volts per meter. Okay. So again, highlighting. It's not the integral side of this formula that is complicated. It's usually the Q enclosed, identifying Q enclosed by your Gaussian surface. Watch out for how that can be tricky and complicated for different problems you're given.